Admitted. Hello, Zoomers. Hello, Roomers. Happy Tuesday, everybody. We have today, first thing to go over the first formative assessment that was due last night. I just updated grades this morning. And then we will go into lecture 4 and example 4 and do our best to get those done this week. And just in case you were thinking to yourself, you know, I really wish I had something else to do for Lisa's class, I'm happy to tell you, you do. I put up your first homework and the next formative assessment yesterday, so you can start working on those things whenever you'd like. So the first thing that's due is there's another formative assessment due next Monday, and then the homework is due 2 weeks. The homework is over what we are covering this week in class, actually. So you're not expected to have known it yet. And I just found a typo that I corrected just a few minutes ago, but I will tell you more about that as we get into it. So to start with, how about we do formative assessment number 1, go over the answers, sound like a plan? Ease our way into things, as it were. So synonym time. Everyone did very well with these first 2 questions, so give me all the things you can think of that go with level 2. Who wants to start? Give me one, somebody.
Between person.
Between person, yeah. So in this class, we're talking about occasions as being treated as nested within persons specifically. So yes, I will take between person as level 2. What else you got for me?
Schools?
Not in this class.
Okay.
Unless you want to say that schools are being measured repeatedly,
Okay.
in which case I'll take it.
So we can say teachers that control a classroom and its students that also take tests.
So in the context of a longitudinal design specifically, that's where we're going.
Okay.
Because it gets very confusing to switch what levels mean across different sampling contexts when you're first learning this stuff.
Okay.
So anything being measured repeatedly is level 2. We'll take that. It can be people, it can be schools, it can be teachers, etc. What else? Inter, yep. So inter-unit differences, yep. What else?
Time invariant.
Time invariant, that's another one.
Macrostructure.
What'd you say?
Macrostructure.
Macro, yep, that's a sort of a classic multi-level term. What else? We got inter-individual differences from the chat, yes. I can think of a few more. What's the opposite of longitudinal?
Cross-sectional.
Cross-sectional, yeah, level 2 is differences that were already there, especially if we're talking about representing level 2 in the model for the variance. Yes, indeed. In terms of notation, is U or E level 2?
U.
U, yes. U is for you. The differences between you all, the people. Yes, indeed. Is random or residual used to refer to that U?
Random.
Random, yes. And I will be very consistent in saying it that way because some textbooks use the term residual for both, and I find that very confusing. It is a random effect. Yes, indeed. Effect meaning a more general term. Intercept is the kind you know so far. Slope is coming next week. I think that's all that was in my head for that. Any questions? Clarifications? All right, well then let's do level 1. All the words that you know that go with level 1. Time varying, yep.
Microstructure.
What?
Microstructure.
Yeah, micro or micro. Mm-hmm.
Intra-individual.
Intra, yep, instead of inter.
Residence.
I heard a couple.
Within.
Within, yes, that's a big one.
Could you say random error?
Let's stick with level 1 residual.
Okay.
I'm trying not to use terms that could be either or. I'm trying to be very specific. So level 1 residual. We had a guess from the chat, fixed. So that one I would say is not specific to level 1. The thing about fixed effects is that they can be considered part of the level 2 model if it's multiplying a predictor that's measured per person, or they're part of the level 1 model if they're multiplying a predictor that's measured over time. So fixed can be either. It's really more about the variance side of the model. In terms of different multi-level sampling designs, the term between for level 2 and within for level 1 always works. That is consistent across every context. It's the word that goes behind it that changes, right? In this class, it's between person and within person. If you come back a year from now when I teach the clustered version of it, it will be between cluster and within cluster. But the between and within demarcation always works. Okay, we got, let's see, micro, within, intra, longitudinal, time varying. So this is the part that you get that's extra relative to a cross-sectional design. Level 1E is another one I would put in there. I think that's all the ones I can think of. Any others that I'm missing?
Time-specific deviation.
Yeah, time-specific variation, I'll take that, as opposed to general person-specific variation that holds across time. Yeah. All right, then I will move on. So a random intercept, what does it predict and what is it for? So there's a lot of different ways you can approach this question. What did you write down? I read your answers, so I know what you wrote down, but I'm waiting for y'all to tell me. Go for it.
To allow people to have their own starting point in terms of mean.
Yeah.
They'll all have the same grand mean value.
So I use the term starting point as a sort of a placeholder, but if there are no random slopes, it's mean over time, which would be the same if it were the starting point or the ending point, because the idea is parallel. So yeah, we're allowing each person to have a different mean over time. What does that then do in terms of how we predict variance and covariance? What have we allowed by giving each person their own mean?
Covariance?
Yeah, we've allowed some kind of covariance. So if we have an E-only model where all of the residual variability is in one pile, that's an independence model. That's saying that all of the E's are independent regardless of who they come from and when. When we split out the variance that's due to level 1 E residual versus level 2 random intercept, that random intercept induces a constant source of covariance among the occasions from the same person. Constant being the operative word. So it's like saying the only reason the occasions were correlated is because some people have higher means than others. And once you control for that, meaning once you account for that variability due to U0, the random intercept variance, then what's left, the E's are independent, if that's the right model. Random intercept goes with level 2 or level 1? 2. Yeah, random is always level 2. Residual is going to be level 1. Yes, indeed. So the idea of random intercept is useful from a descriptive point of view because it allows us to think about how much of the total variation in an outcome is actually cross-sectional, would have been there in a cross-sectional study because some people are just higher than others, versus how much of it is actually longitudinal and reflecting some kind of within-person change or variation. But behind the scenes, what it's doing is introducing person dependency into the model. So we're no longer assuming that residuals are independent. We're assuming that they're conditionally independent after controlling for the random intercept. Okay, I think everyone's answers had some flavor of that. Any questions or clarifications I can help with on that point? Nope? Cool. All right, moving right along. 3 kinds of ANOVAs. Okay, first question then, what do they have in common? I'll tell you the 3 kinds: between person, univariate repeated measures, multivariate repeated measures. What all 3 of them have in common?
Saturated means.
Yeah, saturated means with respect to time, or alternatively in the chat, treating time as a categorical predictor, yes. So an ANOVA model doesn't try to model a trajectory of change. It just says, what's the mean at each occasion? Okay, go with that. So there are as many fixed effects as there are separate occasions to be given a mean. It's one mean and a bunch of mean differences in the way that it's usually parameterized, but it works out the same. So all of them assume that time is discrete, which then also translates into the idea of balanced time. Remember what balanced means? Everybody's on the same schedule. So ANOVA doesn't have room for time 1.5 and time 2.7 because time is treated as a category. You'd have to round them into a nearest interval and introduce measurement error. What kind of estimation are people typically talking about if they use the word ANOVA?
Ordinary least squares?
Yeah, least squares. Sums of squares within, sums of squares between, sums of squares residual, blah, 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 blah. So that restriction of using least squares, in turn, requires what about the data from the same person?
No missing data.
No missing data. Yeah, so not just balanced, but complete. So those are the limitations of ANOVAs with respect to most longitudinal data. How do they differ from each other then?
In the model for the variance?
Yeah, they have a different model for the variance. What's between, say? What kind of dependency does a between groups ANOVA allow of the ease?
No dependency?
None. Yeah, it's assuming that the time predictor would essentially be happening to separate people, which doesn't make sense. How about univariate repeated measures ANOVA?
Compound symmetry?
Compound symmetry, because it uses a throwback to question right before it.
Random intercept.
Random intercept, yes. Compound symmetry is U plus E. So the kind of model for the variance that univariate repeated measure says is all the variances are the same across time, all the covariances are the same across time, and because the only reason for covariance is person mean differences driven by that random intercept. So that's not as wrong for longitudinal data, but it's going to be wrong in a lot of cases where people change. What kind of change does that predict across people?
Constant?
Yeah, the same, parallel. So if people change differently, the variance has to change over time with it, has to. So univariate repeated measures does not address that. Last but not least, the multivariate version of repeated measures ANOVA. What kind of model for the variance is that? Starts with a U, or I'll take a gesture. The gesture is,
Unstructured?
yeah, unstructured. And what do I mean by that?
Whatever.
Whatever, exactly. More specifically, every unique occasion has a different residual variance. Every unique pair of occasions has a different covariance. So it's not trying to pattern anything. It's letting the data be whatever it wants. Now, if you have complete data, you would get the exact same result from just running a covariance matrix where each occasion is given a different mean. If you have missing data, though, it won't be exactly the same. But this is only possible to estimate if you have balanced occasions, though, because it's as many different variances as you have different occasions. So that is a restriction. When else would you run into trouble estimating a multivariate repeated measures? Not just balanced data. Any ideas?
Missing? Missing data?
If it's least squares, yes. If it's some kind of maximum likelihood, then no. You get to keep whatever occasions you do have. Is there an upper limit on how many occasions? Kinda. Yeah, so every occasion adds another variance and however many covariances with the occasions that are already there. So where it starts to break down as a reasonable choice is when you have a lot of occasions and not very many people. If I were doing like a pre-test, post-test design or something where there's only 2 occasions or maybe 3, absolutely I would just go with this and call it good. Let each occasion have a different variance, let each pair of occasions have a covariance, whatever. It's when you have a lot of occasions or when you have unbalanced occasions that this is not going to work. All right, any questions on that? All right, then the last one, the theme song. So thank you all for playing along. I found some interesting new things I had never heard before. I built a playlist on YouTube and it is unlisted, meaning that you have to have the link to get to it. It's not searchable. And I put the link to your playlist inside Icon in an announcement this morning. So you can all check out each other's choices. Those of you who are in both of the classes, several of you picked the same song for both classes. That's fine, but I decided I was going to pick a different one. So my theme song for this class is Tom Petty's Runnin' Down a Dream. If you don't know it, it's in the playlist. But it starts with this great guitar. So it's like I want to say mid-90s or something, but it's been on the radio a lot lately when I play it and just kind of spoke to me. So I decided to go with that one for this class. Thank you all for playing along. I appreciate it. All right. So 2 points for writing anything down and giving it an honest try. If you ever miss one of these, you can still complete it for 1 point instead of 2 if you do it after the fact. But the idea is to do it before we go over it as a class so that you can get your best shot at jogging your memory. So, all right, any other questions about that for now? No, we're good? All right, moving right along then. The next thing that I have is lecture 4, which is I had put up for last week and then we didn't get to it, so I just moved it to be for this week. And I have to tell you, this is one of the more abstract topics that I have to talk about. This goes with chapter 4 of the book, and honestly, that chapter nearly killed me to write. It's not fun. It's not. But I want you to be aware of how random effects models differ from some of the older choices that still tend to be referenced in textbooks and to some extent in use. And so some of this is sort of older stuff that I'm teaching you for comparison or historical purposes. It's also a lesson in vocabulary. So there's some new letters to show up that have to go with different pieces of the model for the variance. And believe it or not, even though it's not going to sound like it, this week and what I'm talking about in SEM are actually the exact same things with 2 different sets of notation. So for those of you who are in both classes, I will try to make those connections as they come up. But here we are. Let me get this thing started. So the big picture. So the models that we're talking about this week are options for modeling variance and covariance over time that is arising from fluctuation as opposed to change. So for study designs in which people are just sort of bouncing around their mean, it's not a treatment, it's not an intervention, they're not developing, it's just longitudinal of like that kind. So smartphone studies or intensive designs, what used to be called daily diary studies, those kinds of things, that's what we're talking about. So in terms of effects of time, we may not even have any. Like in this picture, if I were to try and estimate a slope for the best fit line across this x-axis, it might be flat, because time doesn't really matter from a developmental or intervention perspective. I have a question, did I start recording yet? I think I did. Yes, I did. Thank you for the question. Always good to remind me. So the models that we're looking at don't have time in them. Not as a predictor anyway, because it's not necessarily relevant. If you were to have a design where you didn't think there was change over time, but actually when you looked at the means, you found out that there was, then you would be over here on the left-hand side, the stuff that's happening starting next week. So our objective is just to figure out what kind of model for the variance is going to fit in terms of differences in variance across time and potential differences in covariance. And so here are the choices that form the boundaries of what is the simplest possible model that we would entertain for longitudinal data and what is the most complex model that we could possibly entertain. So you've met both of these already. We have compound symmetry on the left here, and how many parameters are in a compound symmetry matrix regardless of how many occasions? 2. That's what makes it parsimonious. Doesn't matter if there's 2 occasions or 10. There's only 2 things in it. There's level 2 random intercept variance, that's this tau squared thingy right here. And there's level 1 residual variance, of the variance of the e's. The sum of those is supposed to yield the total variance at each occasion, which this model says is constant. The covariance is only due to the random intercept. The only reason why residuals from the same person were related is because of constant mean differences. Once you take that into account, there's no more relationship. So that's why this variance right here is what the model says the covariance should be. So this is our friend univariate repeated measures ANOVA. It's also known as a random intercept only model in a lot of multi-level modeling contexts. On the other side, the best possible fit as indicated by log likelihood is our friend unstructured. So that's the everything gets to be what it wants. There are a lot of parameters potentially increasing as you add occasions. So in this case, there's 4 occasions shown. So I've got a separate variance for each occasion and a separate covariance for each pair. That's 10 parameters. So if you're in least squares ANOVA land, these are your choices. Either everything's the same or everything's different. That's dissatisfying, isn't it? Can't we have some kind of middle ground? Yes, we can. Through the magic of maximum likelihood, we can. So exploring the middle ground here is what we'll be doing today and next week and the week after that probably. Different choices that hopefully do as good a job as unstructured, but use fewer parameters than letting everything but be what it wants. So we're looking at alternative covariance structure models this week, and then switching to random effects models, random effects of time, which are also models that put you somewhere in the middle here next week. So our focus is really on, let me come back here, come back. Basically, are these variances all going to be the same or not? And are these covariances all the same or not? And if not, can we put a pattern to it that captures what it actually looks like and come pretty close to this unstructured? How do we know if we're right? It's always an empirical question. So just reviewing, assessing model fit and assessing whether or not we need a more complex model than what we currently have. So nested models, in which one is a subset of the other. Most of the things that we'll look at this semester are going to involve a nested model comparison. If we're talking about nested models that differ in their model for the means, so fixed effects, like which predictors should I put in, that kind of stuff, we don't need to do anything with respect to log likelihood. Every new predictor that we add has a fixed slope, and we'll get a significance test for that slope on our output automatically. If we want to lump a set of predictors together, such as all of the different contrasts that form a categorical predictor, or say two slopes and their interaction to come up with some kind of composite hypothesis, we can ask for an f-test that lumps slopes together. So all of the nested model comparison stuff that we're talking about here is on the variance side, not the fixed effects side. When we're talking about changing the model for the variance and deciding what fits our data best, we do need to refer to log likelihood or -2 log likelihood as the height of the model. So we're assessing relative model fit at a minimum and what's known as absolute model fit if we're able to fit an unstructured matrix, meaning we have balanced data. So on your output, this differs across programs, but in SAS I've added an option called Cove Test. In Stata you get a confidence interval, and in R it depends on whose package it is, whether you get a confidence interval or a standard error. But my point in telling you this is that there may be a p-value that shows up next to a variance. Ignore it. You can't use it. The problem is that that naive p-value is assuming a null hypothesis of 0 for the parameter and a symmetric sampling distribution around it. But what's the smallest variance you can have?
0.
0. So if 0 is the middle, we can't possibly have a two-sided sampling distribution. So the closer a variance gets to 0, the more important a test would be to see if you actually need it, and the less well those p-values are going to work. So any question that we have about whether we need an extra source of variance is going to be answered by a model comparison involving the model's -2 log likelihood. We can't trust the p-values. Now you can trust p-values for things like correlations if you introduce a correlation into the model for the variance, because correlations are two-sided. So there's some debate about that, but in general, you can't go wrong with your model for the variance comparing log likelihood. Answer a question as to what is necessary. So reviewing what we talked about at the end of class on Thursday, is that okay? A little bit of review for that, maybe? So we're talking about assessing relative model fit in most cases. Is one model better than a comparison model? And just as a reminder, we will get into the technical details of where these numbers come from in a couple of weeks, but I just want you getting used to the concepts. So big picture, how well the model parameters recreate the data is indexed by a height, which is log likelihood. And it's the combined height across all the observations from a sample where bigger is better. So how the model decides which parameters to spit out as the most likely estimates is based on trying to maximize this height. So it'll try out a set of parameter estimates. Let's say that my random intercept variance is 10 and my residual variance is 2. Okay, if that's true, then how tall is the data? Okay, this tall, great. Now, what if my intercept variance was 10.5 and my residual variance was 1.5? Now, how tall is it? And it goes through and tries to figure out what combination makes everyone's data the tallest, and that number shows up on your output as log likelihood. The absolute value of log likelihood is meaningless. You'll get some number like minus 2006. That doesn't mean anything in an absolute sense. It only has meaning relative to other possibilities. There are two flavors of log likelihood, and it's two different formulas by which height is computed. There's what I call regular flavor maximum likelihood, shortcutted as ML in this context, ML, versus residual or restricted maximum likelihood, which is REML. So in this class, we are going to stay in REML whenever possible. The reason for that is because the versions of the random effect variances that you get out of REML are accurate. The ones that you get out of ML are too small. The difference matters less the more people you have. But in a lot of longitudinal studies, there's not a lot of people. So whenever possible, you want to try and stay in REML. So which version of height you get on your output varies by program. Some programs give you LL directly, where bigger is better. Other programs multiply that LL by -2 in anticipation of doing a model comparison. And if it's -2 log likelihood, then smaller is better. Cough, cough, homework question. So they go in different directions. So in our case this week, we're asking basically a couple questions. Does the variance of the residuals differ across occasions or not? And how are the residuals from the same sampling unit, person, if it's measured repeatedly, correlated? Not correlated, all the same correlated, correlated differently over time, differently in a pattern, etc. So we're going to use these likelihood ratio tests, otherwise known as deviance tests or chi-square tests, where we compare the log likelihood between alternative models. Either way, it is fewer minus more. So it is the log likelihood or the -2 log likelihood from the model that has fewer parameters in it, the simpler model, minus the value from the more complex model. So in your first homework, which I have put up, it's actually not a data analysis. There's no data. What I am giving you are -2 log likelihood values, and I'm asking you things. And there are a series of multiple choice questions about which of the following models would result in a valid comparison. This is one of the things I'm looking for you to notice. Is it fewer minus more, which in case good, or is it more minus fewer, bad? Then you'll end up with a negative value, and chi-squares don't go negative. So the result of this comparison should always be a positive number. Otherwise, you can't do it. It's backwards. For the number of parameters, that also needs to be a positive number, so it's more minus fewer instead. What this boils down to is how much taller did that additional parameter make your data, where taller is relative to a chi-square distribution. So I will show you in all of the programs how to find these things. There's also an Excel sheet that I made. The chi-dist function, among others, will give you an exact p-value that corresponds to this likelihood ratio test. In addition to likelihood ratio tests, you get AIC and BIC. And so part of your first homework, I referenced this slide specifically. I'm asking you to calculate AIC and BIC for a couple different models given certain names. Now, I know that you all can work a calculator. That's not the point of this exercise. The point is a vocabulary drill, because you have to figure out how many parameters must be in the model according to what I've called it. So if I say a saturated means model with unstructured variances for 5 occasions, you've got to count all those up. So if it's 5 occasions and it's saturated means, I know off the bat there's 5 fixed effects for the means. And then if it's 5 occasions, I know there's 5 variances, and then however many covariances, I think it's 10, does that sound right? Or 15? 15. Yeah, there's a rule. You can figure it out if you don't want to count. So I'm looking for you to figure out that much, and then to remember, because I asked for an ML versus REML, which ones count. If you are in REML, Only the variance side counts. The mean side does not. So there's all these rules that go with the vocabulary, and that's what I'm looking for you to get a chance to practice for your first homework. So the calculations are an excuse for you to recognize the vocabulary and the rules as to what gets compared versus what in which estimator. Yes, sir?
So does an empty model estimate one parameter, or is it however many occasions there are?
For an empty means model, and that's why I call it that, it's only one because there's one fixed intercept.
Okay.
So it doesn't matter how many occasions there are. If it's empty, there's nothing in the model that allows differences over time.
Okay.
Yep, so there's fixed effects, which at this point you only know two flavors. There's empty or saturated. And then there's model for the variance, which you're going to have a whole bunch of choices for.
Okay.
Yep. And then in terms of talking about what the results of your likelihood ratio test means, if you added parameters, you can say that the model fits better if the test is significant. If you added parameters and the test is non-significant, you'd say the model is not better. Didn't help. If you go the other way, if you're thinking about a comparison, can I get away with simplifying? If your test result is significant, no, you cannot. You made it worse. If the test result is non-significant, it's not worse. And that, by the way, is all of SEM model fit, not worse, relative to the most perfect model. So we will do that in a comparison of unstructured in this class in exactly the same ideas. Okay, I think, yeah. All right, how are we doing so far? Cool. Any questions on this so far? Good. All right, let's get some choices in there. So, big picture. In modeling fluctuation over time, time may not matter with respect to the model for the means. People aren't changing. They're just varying. But it may still matter with respect to the pattern of variance and covariance. So our questions are, basically, are all the variances the same or different? And are all the covariances the same or different? And if different, how? So a couple of notes about what you get on your output. In SAS and Stata, I know if a model has heterogeneous variances, then the way that it will express what the predicted correlations are in terms of, the way that it will express the predicted covariances are in terms of correlations. Because correlation is scale independent, covariance varies by variance. So if you have two occasions that have different variances, then their covariance is going to differ because their variance differs. So you have to kind of separate out from that covariance how much of it is because these variants on a diagonal differ versus how much is because the correlations across occasions differ. So if variances are heterogeneous, it will be specified in terms of correlation. In R, at least within the GLS and LME packages within NLME, it's always specified using correlations. So it takes a little bit of detective work across packages to figure out exactly what you have. I have tried to do all of that detective work for you, but unfortunately they are not consistent in what they tell you. So you have to learn how a model is parameterized within the software package you're planning on using to understand your results. So here are some, what I view as fairly significant limitations for some of these choices that we're going to go over this week. Any choice that is based on the idea of a time lag. So the idea that if I have occasions 1 and 2, that's a lag 1 relationship. 2 and 3 is a lag 1 relationship. 3 and 4 is a lag 1. If I go 1 to 3, that's lag 2. 2 to 4 is lag 2, and so on. So several of these choices have that idea built in, that occasions that are the same distance and time apart should have the same expected correlation. That only makes sense if the occasions are equal interval. So if I have occasions 1, 2, and 3, 1 and 2 is 1 apart, 2 and 3 is 1 apart. But if it's actually like 1 and 2 is 1 month apart and 2 and 3 is 6 months apart, then even though it's 1 unit, it's not the same unit because of the design. So that doesn't make sense. So these start to fall apart if you have unequal intervals. A lot of them assume balanced time as well, because there's no place in the matrix to have time 2.5 or 1.7 or all these intermediate possibilities. The good news is that they don't require complete data. As long as we're in likelihood land, you can use whichever occasions are complete. You don't kick out a person because they're missing one or more occasions. We do have some new terminology to introduce, though, in how these things work. So far, what we have seen is 3 choices for what your R matrix looks like. So this is the notation that I'm using. R, in this case, is the variance-covariance matrix across occasions. And the 3 choices that you've seen so far is independent variance components, so that's the between groups ANOVA where there's no covariance, compound symmetry, which is random intercept only, and multivariate whatever. Now we're filling in more choices for what R is. So this is the repeated option in SAS mixed. It's the residuals option in Stata. It is the correlation structure, and then the variance options within R. I'll show you the code for these. These models all typically start by assuming that the same R matrix holds across people, although in reality that's also an empirical question, and you can change that as part of your model. Models that allow different kinds of variance for different occasions or people is something that I hope to get to next semester. Those are known as location scale models, by the way. The idea that you can predict why some people have more variance than others. That's actually a thing you can do, but for now we're starting with just everybody has the same. And the way that these models are described is with a square matrix where the dimensions are n by n, meaning the number of occasions. So if I'm somebody who has 4 occasions, my matrix is 4 by 4. If you only have 3 occasions, yours is 3 by 3. So everybody gets whichever size goes with their data, but the pattern that goes in it, we're assuming, is the same across people. So as a placeholder for what you will see in terms of other letters, the other way of situating our variances and covariances is by explicitly separating out the random intercept variance and then seeing what is left. That is another version of models we'll probably get to those on Thursday, but those models then involve a whole nother series of matrices. There's G, which is for level 2. There's Z, which is the individual values that are going to be getting random effects, and then V is put back together again. So this is a placeholder to give you the idea that there's more to the story. The first set of choices are using only one matrix directly, rather than a combination across the field. All right. So I have a lot of words in here that are trying to fill in the gaps and explain these things, especially things that you want to watch for across software packages. So in the models that we're talking about today, we are talking about all the variance and covariance in one matrix. It's called an R-only model. For those choices, UN always wins. Unstructured is the best you can have. Now, it's only going to be the best according to -2 log likelihood, though, because once you correct for the number of parameters it takes to make that unstructured matrix, AIC and BAC may not like it. So if I tell you that it will always fit best by -2 log likelihood, then will that value be the smallest or the largest across your choices? What does best mean?
Smaller.
Smallest, yes. -2 log likelihood is shortness, not height. Log likelihood is height. All right. So to make this maybe a little bit less boring, I have a couple of analogies I'll give you for this process, okay? Because no one ever woke up in the morning and said, I wonder if my data have a Topolitz pattern or a first-order autoregressive. No one ever woke up and wanted to know that. That has never been a specific aims, like on an NIH grant, right, to know this. But in order to get to the point where we can believe the results that we care about, believe in those p-values. P-values come from standard errors. Standard errors come from the model for the variance. So this is the background work that we have to go through before we do the things we care about to make sure that our model has adequately captured whatever person dependency is there, adequately captured whatever heterogeneity of variance across occasions is there, and heterogeneity of covariance. So this is the background work that we have to do. A couple different analogies I can use for this. Has anyone ever tried to paint in a house before? Or on a house, I guess? A few of you have tried to paint rooms. So like if you watch those TV shows like HGTV and TLC, they make it look like you go to your Home Depot, you pull out your pipe swatch, and then you set it on the ground and you just start painting, right? That is not how it works. To do a good job painting, what do you have to do first? Prime. How about tape, right? We have the blue tape that protects the baseboards and the ceiling. You got to take off the light switches. If you try to go around them, it's going to look like crap. Unless you're a landlord, in which case it's fine, right? I'm still going to get my rent money either way. Yes, fill in the holes from the chat, absolutely. Paste things, sand things, right? There's all this prep work. It's not fun. It's tedious and annoying. But the more careful your prep work, the better your paint job is going to look in the end. And you can't shortcut it. I am a terrible painter. The first room I ever painted, you could see just like globs of paint where it dried on the wall, and it took me like 8 years to finish the whole thing. It was very traumatic. And now I pay people. But there's a technique to it is the point of the story. And so just think of this as like we're covering the baseboards, we're taking off the light switches, we're doing all the prep work to make sure that our actual analysis looks good. And for those of you who do nail polish, it works the same way. You got to make sure that your nails are filed and buffed and take care of the cuticles, and there's all this prep work that happens before you put the polish on. And the process is actually quite similar. So, does that help at all? Yeah, so it's like this is not about hypothesis testing. This is about just doing the prep work to make sure that the painted room, our model that has fixed effects we care about, is going to be believable. Yes, sir?
So if you don't do that, then you run the risk of trying to recreate like a covariance matrix that isn't really fitting the data properly.
Yeah, well, you run the risk of having standard errors that are incorrect. Okay. And they could be too big or they could be too small, depending on how you're off. Okay. And because people typically make decisions about what predictors to keep based on their significance, like if this part is wrong, then you may be led down a completely different path in terms of the stuff that you do care about. All right, other questions? Okay, so in terms of choices here are a list of menu options, okay? That's what this is. Which options you get varies by software package. So for instance, SAS Repeated has like 32 different kinds. Some of them are with respect to time, some of them are with respect to space. There are fewer choices in other packages, but if you know how to code, and you know how to write out a likelihood, you can make whatever you'd like. But choices that are built in, here's one that you already know, compound symmetry, where if you fit this in SAS, it labels the random intercept variance as CS, but it's in one matrix here. And so no matter how many occasions you have, this is 2 parameters. The alternative with respect to the diagonal is something called compound symmetry heterogeneous. So in this choice, you're allowing a different variance for each potential occasion. You are allowing a different covariance, but only because the variances are different. This CSH thing here, this is a correlation. That is a correlation that is estimated and assumed to hold throughout all the data. And that correlation, that CSH, is multiplied by the standard deviation for each of the associated occasions. And so that then creates the covariance. So it's saying, no, the residuals are equally correlated over time. It's just that they look like they have different covariance because the variances are different over time. So in terms of how many parameters this would take, it's n plus 1. Lowercase n is the number of occasions because you have one separate residual variance for each occasion. And then the plus 1 is the common correlation parameter, that's CSH. That's one set of choices. So in terms of another analogy that I like to use for these is I think of this as different types of pants. Okay? Stay with me here. Unstructured, the whatever model, that's like sweatpants or athleisure. Like it's always going to fit. It's stretchy, there's plenty of room for it to be whatever you want, sweatpants, no problem. This is like skinny jeans. Not everybody feels good in skinny jeans, and it's not comfortable for a lot of different bodies or different data types. But this is simple, straight. This would be like a flared version of skinny jeans or something where you have like potential for different wideness based on where you are in the matrix. Another choice that you will see referred to is autoregressive, first order autoregressive in particular. This one also has only 2 parameters no matter how many occasions you have. So it is as parsimonious as compound symmetry, but it has a different pattern to it. This one has equal variances on the diagonal, but the way that the correlations are put in here is as a function of a common autoregressive R, one number. So this model says that occasions that are 1 unit apart have a correlation R. So 1 and 2 is R, 2 and 3 is R, 3 and 4 is R. Then it takes that same R and squares it for occasions that are 2 apart. So 1 and 3 is R squared. 2 and 4 is R squared. 3 and 5 would be R squared. 3 occasions apart, R to the 3rd power. 4 occasions apart, R to the 4th. So there's only one R. We square it, cube it, fourth it, etc. to get to all of the distant time lags. So the covariance that ends up here in these off diagonals is created by multiplying that correlation times it would be the standard deviation of each of these, which works out to be just that same total variance again. So the covariance here is built out of these 2 terms. And just like for compound symmetry, there is a heterogeneous version that allows different variances on the diagonals too. So if you don't see any words, like homogeneous is the default. Heterogeneous is like an option that adds to it to allow that diagonal to differ. Yes?
Where is that a real world example where you use this?
This is one that I think honestly it varies by discipline. I will tell you that in real longitudinal data, I have never once seen this fit. Never once. Maybe with like cows or amoebas or like other contexts, maybe, but I never have. So I think of this one as tapered genes. So many of you were not alive in the 80s. Let me explain to you what happened in there. The genes were very wide at the top and they got very narrow as they came down to your ankle. And that wasn't narrow enough for us. We actually rolled our genes. I can't do a demonstration because I'm not wearing jeans today, but with a peg roll, where you tuck it over and you roll it up a little bit to make it super tight. And I used to watch this show called What Not to Wear on TLC, where they would like pull people aside and like give them wardrobe advice. And the creators of the show always said never wear these tapered jeans because they're very unflattering because they just narrow too much and it makes the rest of you look really, really wide by comparison. This matrix narrows too much. That's why I think of it as tapered genes. Because let's say that you have an R of 0.8, for instance. What's R of 0.8 squared? 0.64. Okay, what's R to the 3rd? Even smaller. So you can have a very, very strong R that is predicted to decay really rapidly, exponentially over time, such that by the time you get out to lag 4 or 5, this model predicts they're not related at all. That doesn't happen. Occasions from the same person, even if they're really far apart in time, are going to be related.
I can see that working in like medicine, like if you're trying to, like how long it stays in your system or something like that.
Yeah, something like that, like the half-life of a drug or something like that. I can see that working. But in terms of data where it's observational and people come into it with different levels of whatever you're studying, the fact that you have those mean differences, it's going to make occasions that are far apart still have a strong correlation. So I have not seen this work, but you will see people ask, well, have you tried an autoregressive structure? Like I've gotten that from reviewers before, and I'm like, yeah, it didn't fit. So tapered pants narrows too much. You can allow the variances to differ if you want to, but the same issue happens with the correlations narrowing over time. So if it's the heterogeneous version, just like compound symmetry, it's n+1 number of parameters for this one. 2 more, and then I'll show you an example. Toplets. So I always say this wrong. It's toplets. And I always stick an extra syllable in there. Toplets. So bear with me. This one is also known as banded. And it works on the idea of a time lag as well, except that it doesn't have an exponential relationship between the correlations of different lags. So this C is the covariance between occasions 1 and 2, 2 and 3, and 3 and 4, because they're all supposed to be 1 apart. A different C is estimated for the covariances that are 2 lags apart, 1 and 3, 2 and 4, 3 and 5, etc. And yet another C is estimated for lag 3. So this structure has n parameters to it because there's one for every band of the diagonal and off diagonal. So Toeplitz 1 would be just the variances. Toeplitz 2 adds a covariance between occasions that are 1 lag apart. Toeplitz 3 adds another lagged covariance, and then this gets us to Toeplitz 4. So n order would be all of it. So the whole matrix is filled out with this stuff. And then there's a heterogeneous version. So I think of these as like bootcut, because they don't narrow as much. But if you go shopping for bootcut genes, some of them are straight, some of them are flare. You kind of don't know what you want to get. So the covariances have room. Like there's nothing that says the covariance has to be stronger for lag 1 than lag 2. They're all separate. So there's some heterogeneity in what happens according to the data set. So these are the choices so far that we have for R only. There are others out there, but these are the ones that I see discussed most often for longitudinal data. Okay, how are we doing? So something to note. In terms of between versus within, compound symmetry is the only one that does that. The total is made of 2 pieces here that correspond to compound symmetry is the level 2 between part, residual variance is the level 1 part. For autoregressive and for Toeplitz, there's no between versus within. It's just total. That doesn't make it wrong, but it can be less convenient for figuring out how much of the variance is because people differ from each other and how much of it is because of occasions differing. This one doesn't care. It's just a pattern, and it tries to put everything in one matrix without making that level-specific distinction. So this is still modeling person dependency. It's just saying it has a different pattern. Compound symmetry says the dependency is constant. Autoregressive says the dependency decays. And Toeplitz says it decays, but I'm not sure how much. We're going to estimate it. Okay. Let's see some data. Example 4 I have here, and this is real data, which is why the data set is not included in your download packet. For whatever reason, my blocks here are moving all around the screen, and hopefully your version of this looks a little bit better. But these are real data that I talked about for those of you who came to the workshop this summer that I did at the end of May. I'll remind the story for those of you who didn't hear it. These were data collected for a friend of mine when I was a graduate student who was a clinical psychologist, and she was studying the role of forgiveness and coping behaviors in helping people manage how their stress affects their psoriasis severity. So the outcome in this is a measure of how severe each patient had with respect to a skin condition known as psoriasis that's thought to be exacerbated by stress and other kinds of environmental factors. So this is what is known as a spaghetti plot, or if you're writing it up for a paper, this is a plot of individual trajectories. Do not use the word spaghetti in a paper. But it's called a spaghetti plot because like if you took like a handful of spaghetti and just like threw it at the wall, like this is what you would get. Rainbow colored spaghetti, of course, but you know. So in her project, she was going to do this nice, happy cross-sectional study where she was going to measure at a given time point people's levels of forgiveness and coping and their stress and psoriasis and do these nice little regressions. By the time she left her dissertation proposal meeting, her committee had convinced her to do a longitudinal add-on to her proposed dissertation. And I was one of the research assistants who helped to run this study, so we mailed out packets of questionnaires to patients at a dermatology clinic who were being seen for psoriasis over an 8-week period, measuring their weekly stress, their weekly psoriasis, and a few other outcomes. So her question was basically, if you have a stressful week, does that show up in your skin? That's what she wanted to know. Or is there a lag? Like, does it take a week for it to show up? Does it take 2 weeks? But in order to answer that question, we have to focus just on what does the pattern of variability just for the outcome, psoriasis, look like? So the outcome is severity, where worse corresponds to higher numbers. So this example then is just focusing on modeling the pattern of variance and covariance, because as you can guess from this heavy black line here, which are the means, there's no change on average. These patients are being treated, but it's not like the beginning of the study was without treatment. Like, this is just an observational design. So I'm modeling weeks 2 through 8 of this data set because, for reasons, I'll just say that for right now. So there's 7 occasions in total. I am treating the data as balanced because I did not have information about exactly when they completed each observation, so I'm just pretending that week 1 is week 1, and 2, and 3, and 4, and 5. So here is then our answer key model. You've seen the code for this before to fit an unstructured model. So type equals UN is the option that you need in SAS. So sub ID is my level 2 identifier. Week is going to be my level 1 identifier. And this is allowing an unstructured covariance matrix across weeks. Let it be whatever it wants. So this is the answer key with respect to the model for the variance. This is as good as it gets. You can only do this when you have balanced data. So in, let's see, here it is, the word unstructured in the Stata code as well. And in R, it's these 2 pieces. Correlation, that is unstructured, and then the weights option, that allows the heterogeneous variances by week. And I note that R was throwing all kinds of errors at first, and then I figured out that it did not like week starting at 2. And once I made a new version where I subtracted 1, it took it. So, fine. It's week 1 to 7. Are you happy now? Yes, I got my output. Hooray. So I am asking for an unstructured matrix. I am asking it to print what is known as type equals marginal. So that is a word that if you're in other classes you may have heard. It's the idea that it's total in one matrix. So to me, total and marginal are synonyms. We're putting all the variance and covariance into one matrix, and we're seeing what the structure looks like. So get var cov prints the covariance matrix, and then core matrix prints the correlation version of it, where the number that goes in the brackets here corresponds to the dimensions. And that was another one I had to try out until it worked. These little boxes are killing me. It doesn't do this on any other computer. All right. Everything's off. Okay, whatever. We're making it work. So first thing here, how many parameters are in this thing? 28. Where did 28 come from? It's 7 variances on the diagonal, and then, yeah, it's n times n plus 1 divided by 2 is the formula, actually. And then we have 21 covariances. And my stupid little box is in the way, so let me see if I can fix it. Almost. There we go. That looks a little better. So the top, this is my R matrix. This is the variance and covariance over time. This is my answer key. So let's just eyeball this. Do the variances on the diagonal that are in bold, do they look the same or different? They look maybe some the same and some are a little different. Different in a pattern or different kind of random?
Random.
Yeah, they're not heading in one direction like the last example. So this is fairly characteristic of fluctuation data. You would expect that the variance would be about the same over time, but it might be a little bit off here and there. The question is whether a model allowing 7 different variances is going to fit better than a model where there's only one. And if the variance differs, that will make the covariance differ, which is why we can look at the correlations over time. And what do you think about those? Same or different as a function of how far apart the weeks are?
They kind of decay.
Yes.
Decay a little maybe, but like, it's pretty strong, right? So we go from 0.9, the lowest one that I can see is 0.73. So this tells me right off the bat that any structure that predicts a strong decay over time is not going to fit. Even weeks 2 and 8 are correlated 0.8. And the reason for that, I can tell from the picture. Some people have worse psoriasis than others. That looks like most of the story here. There's a few people that vary quite a bit, but most of them are relatively flat lines here. So differences in that y-axis. But we'll go through the process of looking for all of these things here. So the model for the means then is empty. I got a fixed intercept. No matter which week it is, this model says the average severity score is 1.5. It's in a log scale, so I'm not even going to try to tell you what that number means, but it has context. So we go through the choices. So that's sweatpants, unstructured, whatever, can't be wrong. Can't not fit, sweatpants will always fit. Compound symmetry, skinny jeans. Type equals CS. In SAS, exchangeable in Stata, and core comp sim with an extra M in R. So now here's the predicted covariance matrix. So the predicted variance at each occasion is the same, 0.8 all the way across. The predicted covariance is the same, 0.68. And if I take that covariance and turn it into a correlation, that is what's on the off diagonals here in our core. So that is my intra-class correlation according to this model. None of the other models have an ICC because none of the other models try to do this between versus within demarcation. But the average correlation as returned from this model is 0.84. So 84% of the variance is between or within? We've got both answers. Yeah, what's the numerator? It's between. 84% is between, which means that 16% is within, which means more is level 2 or level 1? 2. So 84% is because some people have worse psoriasis than others. In other words, relative to what her committee wanted, this study is an 84% waste of time. It is, because she already had a cross-sectional study. So she picked up 16% extra information for all of the effort she went to for this. I know, but she graduated, and that's the important thing. You write it up and you turn it in. So yeah, so this model says the pattern is constant. How do I know if this is good enough? What do I do next? Yep. I've got my answer key. That's unstructured. The question is this one that only has 2 parameters instead of 28 not worse? So I used my handy-dandy little SAS macro. So that is this thing right here, by the way. At the top of the file that goes with this example, I have the macro program. What it takes as input is the information criteria table from the 2 models, and the arguments are fit. So the table that has your fit information from the model that has fewer versus more. You can put them in any order so long as you label your arguments. So that answer then is right here. So deviance difference, that's my chi-square, is 156 on 26 degrees of freedom. It's 26y. Yeah, it's 28 versus 2. Right? That's the comparison. And the fact that this is significant means, yes, this is much worse. So 2, not enough. Okay? Let's try a different version of 2. This is so funny to me because these are actually text boxes. They're not separate objects. The words are in the box. Like that's its job, is to be a text box, but for whatever reason, they're in different places. I don't know. I'm just going to continue to be amused by this. So here is tapered pants. Let's see if we can still use 2 parameters, but do better. Now, AR1, as specified within this version of it right here in SAS, as well as AR1 in lowercase in Stata, as well as core capital AR1, all of those are for equal intervals. But AR1, you can hack it to have unequal intervals. You just have to look for the right option, and I found them. In SAS, it's this one instead. So spatial power is what the first part of this translates to. It's actually a spatial covariance structure, but you can hack it to put weak in there. And then if you have unbalanced weaks, it would do the autoregressive relationship, not assuming that it's equal interval. It'll do it correctly. Same thing in R. I found this one, core car 1 as an option. That will be unbalanced time for AR1. I couldn't find it in Stata. So here's tapered pants. Its prediction for the covariance over time is pretty much, the variance over time, excuse me, on the diagonal is pretty much the same, about 0.8. But let's look at the correlation pattern. So the way this model works then is illustrated in our core. So 0.8955, that's R. So all occasions that are 1 unit in time apart are supposed to be correlated 0.8955. If I take that number and square it, that's 0.80. Then R cubed is 0.7, R to the 4th is that one, and so forth. So this predicts the correlation to decay down to 0.5 at the last occasion, the highest lag, and in the data it was still 0.8. So this isn't going to work well, I can tell you that right now. How do I know that officially? Likelihood ratio test. So still 26 degrees of freedom because AR has as many parameters as CS. Cough, cough, homework question. If 2 models have the same number of parameters, can I do a likelihood ratio test?
No.
Nope. What can I do?
Information criteria?
Yep, AIC and BIC, smaller wins. So you can't compare AR and CS by likelihood ratio test because they're both 2 parameters. They just do the 2 differently. They both have a total variance, but then they have either a constant correlation or a decaying correlation. All right, one more, toplets. So this is another one that I had some difficulty matching across programs. It is not a predefined structure in GLS and R, so I don't have it. Now, I'm not saying that you can't do it. I'm saying it wasn't a choice I could find. It may exist. Someone may have written their own thing to make it, or you can do it by hand if you configure a matrix or something, but I wasn't going to go to that trouble. Now, note this difference in SAS, TOPE 7 versus Stata TOPE 6. It's the same model. Stata doesn't count the diagonal of variances, but SAS does. So in your homework, when I'm referring to a topolets model, the instructions say use the one that SAS does, because that is counting everything that's in the matrix. TOPE 1 is the diagonal of variances. TOPE 2 adds the first off diagonal. TOPE 3 adds the second off diagonal. And so TOPE 7 is all the way through all possibilities in this 7-dimensional matrix. So this one, then, still has constant variances over time, around 0.8, just like the others. But now it is predicting a covariance pattern that depends on which lag you're on. So this is bootcut, because we're not exactly sure how much it's going to narrow. It's based on the data. So 0.72 is every number right here, because the model says occasions that are 1 unit apart covary 0.72. So it's specified in terms of covariance. 2 occasions apart is 0.69. So that's just a whole separate parameter. That's not squared or anything. It's just separate. So there's 7 parameters in here in total, 1 for each diagonal or off diagonal. Those constant covariances translate into this pattern of correlation, where the only constraint is among the occasions that are the same distance apart, within and off diagonal. And I have labeled what each of these parameters means here in English off to the right. So what do you think about this?
So is it like a stepwise difference between the correlations for for the topels?
I would say no, because they're just separate.
Okay.
There's no requirement that they decline over time or that they're functions of each other. They're just literally separate numbers being estimated.
But the autoregressive does.
The autoregressive does, and that's why this has more parameters, is because this 0.86 is not the first one squared. It's just a separately estimated parameter. So this one has 7 parameters to it, 1 for the diagonal and then 1 for each unique off diagonal. And if we look at this, this doesn't look so bad. It doesn't predict that the correlation decays super a lot for between the first and last occasions. It's not terrible. So let's look at how it fits relative to unstructured. Move the box out of the way. Ooh. P of, yeah, so how do I talk about that? Yeah, almost not significantly worse, right? 0.047 for my p-value if I'm going traditional here. So it's really close. So it looks like I can save 21 parameters and do almost as good a job. So then I'm like, well, how about if I allow heterogeneous variances? So then that is accomplished by adding the H in SAS. So that's a structure that's built in, and it's not built into the other packages. So if I do that one, then I allow different variances across occasions. So rather than having 1, I have 7. So this adds another 6 parameters. The model parameters then are specified in terms of correlations for the lags rather than covariances, because the covariances will differ if the variances differ. So this looks reasonably close to what the data say. I'm not going to eyeball it though, survey says. So I did 2 different tests here. First test is comparing homogeneous topolets versus heterogeneous. Does adding those heterogeneous variances help? Survey says yes or no? No, not better. Adding the 6 relative to what we just had doesn't help. And in fact, compared to unstructured, we're going in the wrong direction. We added parameters, but they didn't help, and so now our p-value is even smaller. So those are the choices that you often see in older longitudinal textbooks, especially ones written by statisticians. A lot of these things, though, to me, are dissatisfying because they're losing the original distinction between how much of the variance is cross-sectional versus longitudinal. That matters, because these distant correlations of 0.8, how much of that is because of just constant mean differences? And if I get rid of that part, can I just see what's left and see how far the correlations have to go? Yes, I can, and we'll do that on Thursday. So you should be able to do, you don't have to if you don't want to, but the first half of your homework now. No data analysis. It is a vocabulary drill using a few computations and some likelihood ratio test practice. All right, 1:45. Any last minute questions before we call it a day? All right, then I will wrap things up and say, see you Thursday, office hours tomorrow. If you need anything, let me know. Thanks for being here.